So currently, hydrogen is used in the refining industry. And there are several processes in refining like hydrotreating. We are talking about hydrodesulfurization, hydrocracking, deep atmospheric residue conversion. And all these are requiring a use of hydrogen to produce useful products. One of the two things have changed in the refining in the past 30 years. One is we have tons of cokers. So we are trying to minimize the coke formation from the crude. And second is we have started processing heavy crudes, very, very heavy tar sands. So what that happens is in order to make marketable products, useful products, you need a lot of hydrogen. You need hydrotreating because you want to remove sulfur. So even for removing sulfur, you have to put hydrogen so that the sulfur combines with hydrogen to give you H2S. So that's typically uh, how hydrogen has been used extensively in the last, I would say, 30, 40 years. And most of it is because of heavy crude. I mean, what we have started processing. So that's basically is leading to hydrogen. Hydrogen is very light. Molecular weight is only 2. Colorless, odorless, tasteless, non-toxic gas. I think it's a very, very fun fuel. Releases great amount of heat, hot flames, future fuel. The only product of combustion is hydrogen, the water vapors, and steam reforming is one of the major ways in which we are generating hydrogen. So very, very important. And here can show you how the hydrogen demand has gone up in last 40 years. We are almost like 4 times. Every 10 years, the demand is doubling, actually, you can see. And there are 2 major users. We have ammonia and we have refining. If you see the chart, you will see basically the 2 major users. Others are very, very minor. So let us talk about the furnaces now, or the SMR steam methane reformer. We have been talking about end products, and the purpose of steam reforming is to convert hydrocarbon feed into hydrogen-rich synthesis gas. It's carried out in a direct fired catalytic reactor in the presence of steam. So we need to understand what process is taking place. So we will talk about the chemistry of steam methane reforming, talk about catalyst, talk about steam to carbon ratio, operating conditions, and design parameters. So in most of the furnaces, we are heating. We are just doing sensible heating, or we are doing vaporization. But this is a reaction furnace. What goes in doesn't come out. So we are feeding steam and we are feeding methane, but what comes out is hydrogen, carbon monoxide, carbon dioxide, and unreacted methane. This reaction is endothermic. It takes place at high temperatures, and the heat is provided by burners firing downward, sidewall, or upward, depending on the design. So this is basically the steam methane reforming furnace. So typical flow is we take the hydrocarbon feed, preheat it in the convection section, then we do the purification. Now, we'll talk about it, but we need to purify and remove all the sulfur, almost down to 0.2 parts per billion. That's how much sulfur because sulfur is a poison for the nickel catalyst. So we want to remove this thing, then we mix steam, again preheat it up, and then send it into this tubular reactors. This is a tubular reactor. where we are providing heat for the endothermic reaction. And then we, of course, we generate steam at the outlet to recover the heat. But that's basically the typical flow scheme. And the flue gases are cooled down and then vented to the stack. It appears that in future we may not be able to even vent it to the stack. We may be recovering CO2 from these flue gases and then sending only the rest of the stuff, oxygen, nitrogen, and water vapors into the stack. And the CO2 will be sent to the pipeline. So that is the future of flue gases as I see in the next 15, 20 years. So one of the parameters we want to talk about is what is steam to carbon ratio? What does it define? Is it weight of steam to weight of carbon, weight of steam to weight of hydrocarbon, moles of steam to moles of hydrocarbon, or moles of steam to moles of carbon? So I mean, so most of you got it right, actually. I would say steam to carbon ratio is defined as moles of steam to moles of carbon in the feed. That's basically what steam to carbon ratio means, actually. And let's go over and ask you a couple of more questions on. So we have a reaction given over here, which is methane plus water produce carbon monoxide and 3 molecules of hydrogen. It's an endothermic reaction requiring almost 97,000 BTUs per pound. So I'm asking you, what is the steam to carbon mole ratio in the below reaction we just talked about? So almost everybody got it correct. It is 1. So if you look at the equation, we have 1 mole of methane, and that 1 mole of methane has only 1 mole of carbon, and then 1 mole of water, which is 1 mole of steam. So the ratio is 1:1. So if you think about this reaction, the basic reaction which is taking place, theoretically, steam to carbon ratio, what is needed is only 1. But what happens is there is another reaction which is taking place, which is called water gas shift reaction. And if we combine that reaction, we get 1 methane plus 2 water molecules going to carbon dioxide plus hydrogen. So we are generating more hydrogen because of water gas shift reaction. So now here, so well, everybody got it right except one. So it's basically 2. Now we have got 2 molecules of hydrogen combining with 1 mole of methane or 1 mole of carbon. So the steam to carbon mole ratio is 2. And we'll talk about a little bit more that theoretically we only need 2. So why are we talking about 3, 4, 5? So we'll talk about and try to answer those questions in a little while. But let's move on. So we have the feedstock. The feedstock, as we talked about, is methane. So there are 2 commonly used feedstocks for synthesis gas. It used to be naphtha, steam naphtha, and it's still naphtha in lot of places. But now, in the past 5 to 10 years, natural gas has overtaken naphtha as it is widely available and cheaper because of shale gas. We got so much shale gas that there is a big boom in natural gas. There is a big boom in ethylene. There is plenty and plenty. I mean, tons of this thing. So globally, right now, 67% of the hydrogen is produced from natural gas. And natural gas is basically methane with some heavier hydrocarbons like ethane and little bit of CO2, And as we talked about, even methane has only 25% hydrogen. Methane actually has more hydrogen content by weight than naphtha actually. So in a way, it is even better than naphtha. Naphtha has much less, uh, hydrogen than as compared to methane. So we already talked about the first reaction, which was reforming of natural gas. And there we are producing hydrogen. Then another reaction which is taking place is this CO, which is being generated, is reacting with more water vapors to generate more CO2 and more hydrogen. So if we add the two reactions, now this is exothermic reaction. If we add the two reactions, we get methane plus 2 water vapor going to CO2 plus 4H2. So we get more hydrogen, And our aim is to get as much hydrogen as possible. So we get these two reactions and we are generating 4 molecules of hydrogen using water vapor. So that is the net reaction which is taking place. So this is a water gas reaction, what we call it, shift reaction. And they both combine to give you more hydrogen. So typically out of steam reformer, what comes out of steam reforming is the gas, which is a mixture of hydrogen. If you see, predominantly we get about 47% hydrogen. Then we get carbon monoxide, we get carbon dioxide, we got methane, we got water, and some nitrogen. So that's basically the output of steam reformers. And if you compare this with different uses, you will see some very good similarity, Now, steam reformer does produce a lot of CO2 for as a side product, So these are the three major industries where hydrogen steam methane reformers are used. And you will see over here, methanol has a different operating conditions. Hydrogen has little bit different, and ammonia has different. The major difference you will see in hydrogen and ammonia is the methane content. Typically, in ammonia, we leave the methane at 8 to 12% because we want to combust this methane to generate carbon dioxide and also get nitrogen. So we do a secondary reforming process and we also generate more hydrogen. So during the secondary reforming, we need this methane. So as a result, the outlet temperature of ammonia reformer is lower as compared to hydrogen and methanol. Hydrogen and methanol reformers are operated at higher this thing. Things may change because they are trying to be bringing different technologies like PSA and air liquefaction. So then the source of nitrogen may change. But this is basically, if you see the difference in minor difference, over here. We get less CO in ammonia and then more CO in methanol, methanol and hydrogen. So it's a gas phase reaction over a solid catalyst. And we need high energy rates for reaction. The typical heat of absorption per mole of CO and hydrogen is almost like 32,000 BTUs per hour. And out of this, sensible heat to get up to the feed temperature of 1550 is almost like 25%. So that's 25% of the heat what we are supplying is getting into just a sensible heat. And you can see that these are the two molecules, methane and water, and then we get hydrogen and CO2. That's what we are getting. So I just want to give you utility requirements. If you see, for a 50 million standard cubic foot per day hydrogen plant, the feedstock needed is 730 million BTU per hour in terms of energy. Almost 20% is the fuel which is needed. And then it exports steam. So a lot of steam gets generated. And the reason for that is the feed is at ambient temperatures. If you look at the natural gas or methane, it is at ambient temperature. And if you see the products leave the reformer at about 14, 15, 1600 degrees F, but then they have to be cooled so that they can be processed further. We cannot use that 1600 gas anywhere in the CO, methanol, or hydrogen. We need them at the lower temperature. So it has to give out that high temperature products have to give out heat, and that leads to a lot of steam production. So it is not a matter of choice, but as a matter of necessity, because we are going to take the feed and heat it up all the way to 1500 so that the reaction can take place. And then again, we have to cool it down. And also we have to cool down the flue gases so we generate more steam. One from the product, one from the flue gases. So almost 120,000 pounds per hour or 54 tons of steam is generated in a 50 million standard cubic foot per day hydrogen plant. I don't have the number in metric, but maybe next time we can put this number in metric also, 50 million. So let's talk about how we are designing reformers, or what are the parameters which are responsible for converting the methane into hydrogen. And we talk about three parameters here. We talk about temperature, we talk about pressure, and we talk about steam to carbon ratio. So three parameters we want to talk about. And this is a chart which we have put. Basically, we have pressure, we have temperature, and we have steam to carbon ratio. So these three parameters, if you use, you can go whatever is the temperature, let's say 850 degree and 35 bars, you go up to 3.5 or ratio, and you can see the equilibrium methane will be around 5%. So you can use this chart to get the methane at the equilibrium, what will be the methane. So basically that's the chart which can help you just look at what will be the theoretical methane which will be in the product on the dry basis. So, but what we talk about theoretical product, theoretical concentration, and we're talking of actual concentration, and between the two, we call it approach to equilibrium. And that means, let's say we get 1500 degrees for getting 5% methane we just saw in the chart. But in reality, you will see that temperature has to be 10 to 15 degrees higher at the start of run. At the end of run, it could be even 35 to 50 degree higher. So that difference in temperature is basically the approach to equilibrium. And that happens because the catalyst keeps on getting deactivated over the time. So the catalyst keeps on getting deactivated. So most of the reformers we will be designing for about 35 to 50 degree higher actually. If we get 1400 degrees outlet temperature for getting the methane, we will design it for 1450 so that you as a client never falls short on the methane. You can, in the beginning, you can run at a lower temperature, and then as the catalyst ages, you go higher. So you can see this is the equilibrium temperature, and this is the gas temperature. So basically, we try to lower approach will get you lower exit methane in the product. So in the new plants, your temperature will be lower, and as the catalyst ages, your temperature will keep on going up. So methane slip, at the start of run, we will be very close to equilibrium conditions, but as the condition at the catalyst starts aging, the methane concentration will go up, or we will have to raise the temperature. Typical operating conditions, steam to carbon ratio of 3:5, outlet pressure of 290 to 550, and outlet temperature of 1500 to 1650 degrees. That's typically the operating conditions, what we have for steam reforming. So if we go for a higher outlet temperature, what will happen to the methane content? Will it go up? Will it go down? Will it not have any effect? So only 2 of 10 people got it right. As the temperature goes up, the methane content will keep on going down. Remember, this is an endothermic reaction. Endothermic reaction means it needs heat. So the more you heat, more reaction will take place. So the methane content will go down. Higher temperature. Okay. So higher temperature will always help our methane this thing, but we have a limit. We have a limit on the temperature, and we'll come to that. But let's talk about more things. We talk about if we increase the outlet temperature from 1400 to by 50 degrees to 1450, methane content will drop from 10% to 7.5%. So we have more conversion taking place. Similarly, if we increase the steam to carbon ratio from 3 to 4, methane will drop from 10 to 7%, 7.5%. If we do both, then it will go even higher. Other thing, if you see, if we decrease the outlet pressure from 400 psig to 300 psig, methane content will drop from 10% to 8%. So you can see the parameters which are affecting the methane conversion. And it is simple chemistry. The simple chemistry is if it's an endothermic reaction, higher temperature helps. If you looked at the equation, 1 CH4 plus 2 H2O give us 3 molecules of hydrogen plus CO. So 2 molecules, 3 molecules goes to 4 molecules. That means the volume is increasing. So anytime in any reaction, if the volume goes up, the lower pressure will help. So if you decrease the pressure at the outlet, it will help. However, it is not commercially viable to work on a lower pressure, and that's why we still continue using higher pressure. Feed purification, we have to have the feed to be really, really purified. We are going to go down to 0.2 ppm on sulfur, 0.2 ppm on chlorine, heavy metals less than 0.1. So we have a zinc oxide bed, and we try to take that sulfur out from our natural gas or from naphtha. And these are the reactions which are taking place. There's hydrogen reacts with the mercaptan compounds, converts it into H2S, and that H2S is absorbed in the zinc oxide bed. So it's a very, very established technology which is used for removing sulfur. So sulfur has to be removed. If the sulfur goes to the catalyst, your catalyst will get deactivated. So we have to make sure that the poisons, which sulfur is one of them, does not go to the. There are some other reactions taking place. Let's just go over quickly. One is the hydrogenation of olefins. The important one is carbon forming reactions or CO reduction reactions, because another thing is carbon. Another problem with the catalyst is carbon. If you have carbon deposit on catalyst, your catalyst is gone. The catalyst is a surface phenomena. If your surface is clean, that's where the catalyst is active. If you cover the catalyst with soot, carbon, anything, catalyst becomes deactivated. So it's a very, very simple this thing. So what happens is, if you have got any olefins in the feed, they will combine with hydrogen to make ethane. So you don't want this thing to be happen. So you want to make sure that olefins are removed from the feed gas even before you process it. You don't want to be consuming hydrogen. Similarly, carbon forming reactions are very, very important. There are two reactions we are talking of: methane cracking into carbon and hydrogen. We don't want this to be happening at all. Or the second reaction is Woodard reaction or CO disproportionation. Basically, it happens at high temperatures, and here you can see CO is converting into carbon and carbon dioxide, and that carbon monoxide also meets with hydrogen to convert carbon and H2O. So you don't want these two reactions to be taking place. They could be, if you have carbon formation, you will get problems. So we have to make sure that these two reactions don't take place at all. So let's talk about the function of the catalyst. Why do we even use catalyst? So we could have combined methane and steam, but to combine it, we will need very, very high temperatures, or we will need very, very different conditions. So the catalyst, what it does is catalyst alters the reaction rate. Catalysts do not take part in the reaction. They don't get consumed. They basically lowers the activation energy of the reactant. So if you see over here in this chart, we have reactants over here, and without catalyst, it will be much higher. But with catalyst, we lower the reaction activation energy, and that is why we get conversion. Okay, so without catalyst, we will have to go to extreme conditions, and the conversion may be very, very low.